Hello friends, welcome to lecture number 14. In today's class, we will study about electrostatics of conductors where we will read in detail about the shielding effect and later on we will deal with quadrupole problem. Okay, so let me start today's class with the electrostatics of conductors, which mean the properties of the conductors. The first point is inside a conductor electrostatic field electrostatic field must be we can write electrostatic field is 0. Okay, the second one, at the surface of a charged conductor the electrostatic field must be normal means perpendicular, must be normal to the surface at every point. Okay, moving to the third point, the interior of a conductor can have no excess charge in the static situation. So these are the important properties. The fourth one, as in the previous classes we know E is equals to minus dV by dx, and as we studied from the properties that the electric field inside the conductor is 0, then what will happen to the potential? It has to be constant. If E is equal to 0, V has to be constant. Then what property can we write? That your electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. That means on surface and inside it has the same value. Okay, moving to the fifth property. The fifth one is the electric field at the surface of a charged conductor is E vector is equals to sigma by epsilon naught n cap. Okay, where sigma is the surface charge density. So this is the statement which I have made, but in CBSE this comes for a 2-mark question, that you have to show that the electric field at the surface of a charged conductor is this much. So for this, what I will choose a surface of the conductor. This is your surface of a conductor, and in this surface I will take a Gaussian surface, and the Gaussian surface in this case will be a pillbox. This will be a pillbox as we have taken it in other applications of Gauss law. So this is your pillbox, and it is quite obvious on the surface of the conductor the electric field is up. Okay, so and n cap for this Gaussian surface, the pillbox, this n cap will be along this direction. So this is your Gaussian surface where we have taken as a pillbox. Okay, now we can use Gauss law. Using Gauss law, we can use Gauss law here, that your E summation S is equal to total charge enclosed by epsilon naught. Now you tell me, sir, why E delta S? Because the theta here is your 0 degree, because electric field and the surface or the n cap, they are in the same direction, they have the same direction, as you can see it from the figure. Therefore, E delta S cos theta goes to 0. So total charge is summation Q, and total charge will be how much? It will be a surface charge density into the area, okay, divided by epsilon naught, and here you will have E into delta S. So delta S gets cancelled out. So to avoid confusion, your sigma is what? Sigma is surface charge density, okay. And what is delta S? We are taking a small area of cross section. It is your small area of cross section, okay. Then what will be the electric field? Electric field will be sigma by epsilon naught. This is your vectorial, this is your scalar form. But what about the vectorial form? E vector will be how much? Sigma by epsilon naught, and the direction will be in the n cap direction. So this is your final expression. So to derive this one, you have to draw the diagram and you have to reach up to this much, okay. Here there are few things which are to be noted. For your surface charge density sigma greater than 0, your E vector is normal to the surface, normal to the surface, that to outward, okay. Now for sigma less than 0, your electric field is normal to the surface and it is inward, okay. So these two things are very important, inward and outward, okay. Now the last property, the sixth one, which is your electrostatic shielding. The sixth one is a very important one, which is called as your electrostatic shielding, okay. Since it was found by Faraday, it is also known as your Faraday's cage. It is also known as Faraday's cage, okay. Now what is it? So this electrostatic shielding tells us that suppose I am having a conductor here. I have a conductor here. Now I give some charge. This is a conducting body. Suppose this is a conducting body. Conducting body. Okay. Now I give some charge to this. So let us assume that this side I will have some negative charges. Here I will have positive. And it is quite obvious, if this is negative, your sigma will be less than 0 and the electric field will be inwards, which we have read. And in the whenever it is positive, your sigma is greater than 0. For that, the electric field will be away in this direction. Clear? So what happened? Faraday told that if I am able to construct a cavity in this form inside the conductor, then what will happen? Any excess amount of charges will come. They will reside on the surface only. They will not affect anything which is kept inside the cavity, okay. So it is known as a cage. Now how is it useful? We have got different sensitive electrical instruments. Those instruments can be kept here, and any amount of charge or any amount of excess charge that comes, that will reside on the surface without hampering the body, which is without hampering the electronics equipment which is kept inside the cavity. So this is the importance of this cavity, okay. So let me write. So this is what, this is your cavity which we are taking the help, or which is your Faraday's cage, okay. Now what is this electromagnetic shielding? Let me write it here. So whatever be the charge, whatever be the charge and field configuration outside, comma, any cavity in a conductor, any cavity in a conductor remains shielded, shielded means protected from outside electric influence, Okay, outside electric influence. Okay, the field inside the cavity is always 0. Okay, and this is known as your electrostatic shielding. So I hope it is clear to everyone. This electrostatic shielding, this is very important, which comes in the exam. So we can write, it is useful in protecting sensitive instruments from electrical electrical influence. Okay, so this is all about your electrostatic shielding. Now inside the cavity, what is the electric field? It is 0. Sigma is also 0. What will be the potential? A constant potential V naught. So this is basically, this picture is very important. This picture is very important because all the properties are there inside this picture. So try to remember this one. Okay, now after this I would try to do a problem which is very important and comes in the CBSE, that is your quadrupole problem. Okay, you have understood dipole. Now let us try to understand what is a quadrupole and how it looks like. So let me give a heading. We will start with a quadrupole problem. Okay, quadrupole problem. This is a NCERT problem which is there, question number 22 of chapter 2. Okay, quadrupole problem. Now what is the question? Let us first understand that. There is a configuration which is given to you. There is a charge array which is given to you. The configuration is given to you and asked. Suppose you have got a plus q here and you have got your minus q here. Another minus q there only. It is there and here it is plus q. Okay. So two dipoles are kept very close to each other, forming a quadrupole. So basically this is a charge array which is given to you, which is a quadrupole. Okay, electric quadrupole. And the distance here it is given, it is as a, and this is also given as a. Okay, now it is asking on the axis of this quadrupole, let a point P, it has taken a point P, and this point P is situated at a distance r from the quadrupole center. Okay, so this will be your quadrupole center, so r, right? So it is asking at point P, what will be my potential at point P? It is asking you what is Vp if one condition is given, if r is much greater than a, what is your Vp? You have to find out Vp. Okay, potential at P. So let us solve it. Potential at P will be equal to K, I can take common. Now first I take a charge q, this plus q charge I will take. So charge by distance, so that will be r minus a. Okay, then I will take this one minus q, this will be minus q by r. Again I will take this q, then will be minus q by r. Then I will take plus q here, so that will be plus q by r plus a. I hope it is clear to everyone. You should understand that all the four charges will contribute. Okay, now I see q can be taken common, so I have kq. So what is left out for me? 1 by r minus a minus 1 by r minus 1 by r plus 1 by r plus a. So let us fix it. So what I take, LCM will be r into r minus a, r plus a. Okay, so the first term will be r into r plus a minus 2 times it will be there, because 1 by r is there, 2 times of r minus a, r plus a, then plus r into r minus a. Okay, So this will be. So now let me expand it. So Vp will be how much? Kq. Let me expand it. If I expand this one, what I will have? R into R square minus A square will be there. Now in the numerator what I will have R square plus AR minus 2R square plus 2A square plus R square minus AR. You see, minus AR and plus AR will be cancelled. R square and minus 2R square will be cancelled. What is left out? KQ into 2A square will be left. So what will be my VP then? So everything will boil down to KQ. Then you have 2A square divided by R into R square minus A square. Okay. Now you see here the way in dipole we have dipole moment. Here also we have got your quadrupole moment. QUA DRUPOL, quadrupole moment. Okay. Now how the quadrupole moment is represented? It is represented by capital Q. Don't confuse with the source charge. It's capital Q. Capital Q will be equal to 2Q into A square. Quadrupole moment is defined in this manner. If it is defined in this manner, then in the numerator what I will have? I will have Vp is equals to KQ divided by R into R square minus A square. Okay, is it clear? Now you see here we have to use the condition because it is asking to find out Vp. What is the condition given? R is much greater than A. Okay, we have to use this condition. So if I use this condition, if R is much greater than A square can be neglected. What is left out? Vp will be K into Q divided by R cube. Okay, so this is the expression what it has asked in the question. Now there are few points which you should note. That is very important. You have to keep something in your mind. What all informations you have got here. The first information what you get from this is for large R, when R is going to be very large. For large R, your quadrupole potential varies as 1 by R cube. Okay, quadrupole potential. Then what about the dipole potential? For your dipole potential, it varies as 1 by R square, and single charge is called as monopole. Okay, that is your monopole for a single charge. For a monopole, what is the potential? It will be proportional to 1 by R. So these things you remember, that for quadrupole it is 1 by R cube, dipole it is 1 by R square, monopole it is 1 by R when we talk in terms of potential. Okay, so with this I would like to end the class. I hope everybody have understood. Do like and subscribe the channel. Okay, any queries you have, you can email me in my mail ID which is shown below. And finally, thank you for your kind patience.